Hi, we're going to continue our discussion of thermodynamics. And this focus 2 is really a focus about the first law of thermodynamics. So we talked about heat and work, which are ways to move energy. Now we're going to talk about internal energy. Okay, focus 2C, internal energy. So I'm always assuming that you have your book out because I know you can't read this. So I think it's good for me to use the book though, because then you know exactly what I'm talking about. If anything doesn't make sense, you know exactly where to read a bit more. So the key idea here is that the internal energy of an isolated system is constant. The change in internal energy is equal to and it should be the heat transferred at constant volume, not the energy transferred at constant volume. In that key idea section. So when we talk about the internal energy, we're talking about all of the energy that a system contains. And we label that with a U, and it would be all the energy of the electrons. We know mass is energy. There's a lot of places to have energy. So it's pretty hard to know how much energy a system contains because you're talking about all the potential and kinetic energy. But it's fairly easy to think about how the internal energy changes, we'll see. So in general, we're going to be talking about molar internal energies. So that's just U divided by the number of moles. And so because it's so hard to actually quantitate how much energy is contained, we can think about how energy changes. So the change in internal energy, which would be equal to the final internal energy minus the initial internal energy during some change, maybe a phase transition or a chemical reaction. And because internal energy of an isolated system is constant, that means if the internal energy changes, you have to be able to measure heat and work flowing into or out of the system. So we always know that if the internal energy changes, energy had to move in or out. Work and heat are the two ways for energy to move in and out. So we're going to have to be able to basically find those forms of energy moving. So problem 2C.1 just asks you what's the value of delta U when 10 kilojoules of work is done on a system. And number 2, when 15 kilojoules, and that really should say heat, is supplied to a system that does 10 kilojoules of work. So that is the problem. So in the first one, it's 10 kilojoules of work is done on the system. That means the internal energy goes up. The work you did on the system increases the internal energy, so this is a positive sign. And then the next one, 15 kilojoules of heat is supplied, and the system does 10 kilojoules of work. So if you supply the heat, energy flows in, that's a positive sign. If the system does work, its internal energy goes down, and that's a negative sign. And so the net contribution to the change in internal energy would be 5 kilojoules. So we'll take advantage of this often, that the internal energy of a perfect gas doesn't change unless the temperature changes. A perfect gas has no potential energy, and so if you change the volume, you aren't changing anything. You're not changing the kinetic energy. And if you pull the particles apart, if they're not interacting by changing the volume or pushing closer together, there should be no change in their energy because they don't interact. So in other words, the internal energy of a sample of a perfect gas at a given temperature is independent of the volume it occupies. So particles can be close together, far apart, depending on the volume of the container, but if they're not interacting, that shouldn't change the internal energy. So this is a concept you probably remember from Chem 107, that internal energy, when we talk about enthalpy and entropy later on, those are also state functions. And that simply means that when you say UF minus UI, doesn't matter how you get from here to here, it just matters that you're in those two states. So the internal energy, you could change it by, let's say, up here, maybe variable 1 is the pressure, variable 2 is the temperature. And you can change those in different ways. You could change variable 1 first and then 2. You could do the opposite, change variable 2 first and 1. But if you go from the same initial to the same final state, then the change in internal energy will be the same. It's independent of the path that you take. And your book uses that very common analogy to altitude. Your altitude when you're on top of Pikes Peak is the same whether you came from the Craig side or Bar Trail, or whether you looped around or got dropped off by a helicopter. Doesn't matter. You get to that location and your altitude is going to be the same. So when we think about changes in the internal energy, we know that the energy has to go someplace, so we'll be able to measure those. But if you isolate the system, the internal energy has to be constant. So if you isolate it, you're saying heat can't flow in and out and work can't be done on or by the system. So that is the statement of the first law of thermodynamics, that the internal energy of an isolated system is constant. So if delta U equals Q plus W, and if you carry out the process at constant volume, and the only kind of work is expansion work, you don't allow any electrical work or anything else, at constant volume, work is proportional to dV. So if volume doesn't change, there is no work. And so that means if a process is carried out at constant volume, the entire change in internal energy is equal to Q. And so that's what this notation means. Q, if the process is carried out at constant volume, is equal to delta U. So in a bomb calorimeter, that's exactly what you're going to have. You're going to have constant volume. We'll use this in lab. You burn a sample within this bomb. The volume is held constant as the gases are created in the combustion. And in that process, you can measure the internal energy change by looking at the heat capacity of the bomb. So the change in internal energy over the change in temperature is equal to the heat capacity at constant volume, because this equals QV, and we said that heat capacity is Q over delta T. So at constant volume, Q equals delta U. So it'd be better to think of this as a derivative and not necessarily just a slope, because this graph shows you that how internal energy changes with temperature changes. It's not just a straight line with a constant slope. And so the better way to write this in calculus is to say that the heat capacity at constant volume is equal to how does internal energy change with temperature. And this just reminds us that that's a partial derivative. If we're holding volume constant, it's only the temperature that we're changing. So this is the precise definition of a heat capacity at constant volume. It's the derivative of internal energy with respect to temperature holding volume constant. So when we think about how internal energy changes, we think about all of the places you can put energy within moving systems. So especially with perfect gases, we don't have any potential energy. We just have the kinetic energy. So the average value of each quadratic contribution to the energy is 1/2 kT. And a quadratic contribution is anything that depends on the square of a position or velocity. So such as kinetic energy is 1/2 mv squared, then that would be equal, the average energy of that equal to 1/2 kT. So in translation, we have each kinetic energy term, and in rotation we have kinetic energy terms. And then in vibration, we have kinetic energy and potential energy, because as the molecule stretches and squishes together, the kinetic energy is interchanged with potential energy. And so a vibration actually contributes one for each of these quadratic terms. So when we think about it, let's just work out this problem 2C as an example. 2C. Well, let's see what the problem is. What's the contribution of motion to the molar internal energy of a gaseous H2O molecule? Ignore the vibrations. So we have to go back. I can't believe I didn't work this one out. Oh, yes, I did. I just labeled it wrong. So this is number 2. So oh, no, I worked through number 1. That's why. So let's do a different one. Let's do the example. So this one you can read through, and I'm going to do the one on water. So the water molecule has N equals 3. So we have 3 atoms. So how many vibrations and rotations do we have? So we have 3 N translational contributions, because the water molecule itself can go in the X, Y, and Z directions, so can move in 3 different directions. And how many rotational modes do we have? So it's a non-linear molecule, so we should have 3 different rotational modes. Oops, not 3N. And then it says to ignore vibrations. The total number of vibrations that we would have would be 3N minus 3 minus 3. So it would be 3 vibrations, but we're going to ignore those. And the reason you ignore those is because as energy is moved in and out of a system, it has to go places. But at room temperature, it takes so much energy to excite a vibration that you're probably not going to put energy in there. The vibrational modes will only be important at high temperature, which is, if you read the molecular basis of internal energy, it will talk about that in here. So that means that we have, we want the molar. So we have KT for each of these, 1/2 KT. And then for the rotational, we also have 1/2 KT times 3. So we end up with 6/2 KT per each molecule, which is 3 KT. And if we want to have a mole of that, then we multiply that by Avogadro's number. And so we end up with 3 KNAT, which this equals R, and so you end up with 3 RT is the contribution. And you could actually calculate that, but by putting in a value of R and T if you wanted to. So that's thinking about where energy is stored and how you can change energy when you think about putting it into the different modes within your molecule. So what would CV be for this guy? We take the derivative of this. With respect to temperature, we get 3R. And when you compare that, so this is talking about a monatomic gas. When you compare that to the measured experimental value, you get a pretty good value. So when you're talking about a monatomic perfect gas, then internal energy is going to be a function of temperature. So individual particles can fly through space. but they can't rotate and they can't vibrate. So monatomic. So all they can do is fly through space. And so if we look at per mole, essentially K is the molecule's version of the gas constant. So gas constant is per mole and Boltzmann's constant is per particle. So if we want to see what CV is, so CV changes with temperature. The derivative of this with respect to temperature is 3/2 R. And when you look at that value, and if you actually measure the heat capacity of a perfect monatomic gas, it's almost exact agreement with the value right there. So that is all for internal energy. Next, we're going to introduce the concept of enthalpy in the next lecture.